Lost in the fog of a cosmic storm, floating on whimsical wavelengths is the norm. Dancing through the stars, chasing spectrums of light, riding the waves that are just out of sight.
Welcome back to Whimsical Wavelengths, where we explore the deep underground music scene. Like magma, it forms pretty deep. Yeah, that's a terrible segue into another episode about volcanoes, but this time I've reached out for a favor from a friend to share her research. Before going into the intro, volcanic eruptions are dynamic. The amount of force and material involved in an eruption, it's large. Even if the eruption is small, the changes can be significant to the overall system. Let's go through what a volcanic system is, specifically the plumbing system, or i.e. where the magma is, all that liquid that feeds eruptions. First, the source, where the initial magma was created deep beneath the surface. Specifically, for the subject of today, Negra, the magma comes from hot material upwelling towards the surface. Note, solid material can still flow over long timescales. I don't want to get too sidetracked here, but think of glaciers where solid ice flows over years under its own weight. Also, pressure is lower towards the surface. We've covered this before in previous episodes. And magma, like lots of material, has different temperatures at which phase change occurs depending on pressure. Think of water boiling at elevation. Or if you want a different way of thinking about it, put water in a vacuum. It'll boil at room temperature. This hot material eventually can start to melt due to that lower pressure as it gets closer to the surface, generating magma. That's hotspot volcanism. Okay, then as it forms, it collects into bigger batches of magma. It mixes with other batches of magma. As it continues to rise, it may stop or stall out for some time. During this stall, it'll begin to cool a little and crystallize some. And as those crystals are removed from the rest of the magma, it changes its chemistry. It may freeze or then continue moving upwards, where magma tends to stall, likely due to density and gas solubility. It will then collect in a volcanic system near the surface in what we call a magma chamber. That was a real brief, quick way of going over that, magma evolution can be quite complicated with lots of stops and starts along the way. Magma chambers close to the surface we can see through a number of different monitoring techniques. Today we will focus on gravity and deformation, mass flux, and how the Earth's surface moves in response to changes at depth. So today's guest is someone I know well, a friend of mine, and she will bring her absolute eruption of insight, an igneous intellect, and together we will magma-nify this topic. Today, here at Whimsical Wavelengths, I'm super happy to welcome my friend and past fellow graduate student at Simon Fraser University, where we both use geophysics to investigate volcanic processes. And she just wrapped up a postdoc in Italy, and now I get to butcher some names, which is fantastic. So she, apparently, I was just told that there's 3 universities with essentially the same name. So let's see if I can do it. Sapienza, University of Rome. So please welcome Dr. Antonina Calorano de Petra.
Thank you so much, Jeff. It was almost there. It's Sapienza, which means wisdom in Italian. So
Okay, you've had years of laughing at me putting my foot in my mouth. So the nice thing
we
about
can't break tradition.
No, but it's also a really nice thing about having friends in sciences when running a science podcast. I can effectively generate content by just calling someone up. So the first question, I actually don't know the full answer to, or because we essentially just kind of geek out on volcanoes and geophysics in general. I've never really asked how you came to volcanology itself. Was it something you always knew you wanted to do early, or is it something you kind of discovered or fell into as you started going to university?
Well, it's actually kind of a funny story. I started my undergraduate degree as a physicist, and I actually completed a degree as a pure physicist. I knew basically nothing about geosciences. I was very much not interested, more than the normal person that is surrounded by volcanoes, in volcanic activity and about why or how volcanism worked. However, at some point, in order to graduate for university in Ecuador. I'm originally from Ecuador, from the capital city, Quito. You need to complete an internship that ideally is going to be related to what you want to do in the future. But it's also a way to try to understand what opportunities for working are available to you with your degree. So in Ecuador, there weren't many opportunities for using my degree in physics in the normal, let's say, working environment. But there are a couple of options. For example, there was the possibility to do an internship in a hospital doing some medical physics. There was also the option that most of my fellow students that were doing physics at the time took, which was to try to find a lab outside of Ecuador to do the internship. But that also meant extra time. It also meant that they already knew what they wanted to do in physics, so they knew what to apply for. But there was also, and this is serendipity, as our professor used to say, Kling. My father knew the head of the Geophysical Institute of Ecuador, which is the institute that is responsible for monitoring volcanoes and earthquakes in Ecuador. So at the time, they were looking for students to do internships in the Geophysical Institute. So at this point, even though it was a different university from where I was doing my undergraduate degree, I managed to do this internship in the Geophysical Institute. And usually during these internships, you may be given some really tedious tasks that no one else wants to do. So for example, in a Geophysical Institute, one of such tasks could be to have a lot of seismic signals. So if you can imagine, it's kind of like a little wiggle that starts with a certain amplitude, with a certain height, let's say, and then it tapers off. A tedious job for an intern would be to basically have a lot of these signals and pick the start of the signal of the earthquake and the end of the earthquake. However, just at this point, they had a new instrument that no one was using, which was a gravimeter. So
My favorite, of course.
Exactly, our favorite, of course. So they said, okay, we have no one doing this, but it's a very expensive instrument, and we need to use it, and no one wants to read this manual. So new intern, just read the manual and figure it out. So yeah, it was. It was kind of nerve-wracking because it's suddenly like, oh yeah, this is a $130,000 instrument. Don't break it. Good luck.
Wow. That's not every day. They just kind of hand that over to an intern and say, "We don't know what this does. Figure it out and use it for us, please."
Yeah, I don't know. Maybe they thought I was trustworthy. Maybe they really didn't have anything else for me to do. But I was very lucky that I started with gravity because, first of all, it had a very it was very similar to what I had already been doing in my physics degree. I knew potential fields. I knew how the gravity field behaved. I knew that, okay, more mass, more gravity, less mass, less gravity. But I didn't know how to apply this to earth sciences. And I really liked to having something to tinker with. So that's how it basically started with me just calibrating this instrument, figuring out how to use it, what was the best way to start doing measurements so that they were useful for the Geophysical Institute. And then it just continued from there, looking at applications for volcanoes and even for earthquake and fault detection and things like that. So that's how I started.
Okay, this is going to be a total deviation and unplanned, but I don't know how else to do this. Let's talk about what the gravimeter is. So in this particular instance, for those who are listening, there's a couple of different types. They're all called spring gravimeters, but we're going to cut to the chase and talk about this particular gravimeter itself, what's called the Syntrex Gravimeter 5 or CG5. I'm assuming that's what we're talking about here.
Yes, exactly.
Okay, good. So what is this CG5?
So the CG5 is basically a very, very, very expensive spring. You just have a little spring, a little mass, which is basically a weight attached to the spring. And this spring just extends or contracts. And of course, maybe some of you, definitely I did when I was in high school, maybe you did an experiment either with a spring or with a pendulum that you can measure the gravitational constant of the Earth. So a lot of people know that Earth's gravity is 9.8 meters over second square. However, with the Sintre CG5, we do not measure the 9.8. Yes, we do measure gravity, but we measure 9.87 until all of these numbers, we measure very, very little changes of this gravity field because the gravity is not constant on Earth. Even though at certain levels you can say it's constant, for practical purposes it is, but you can measure little changes either in space or in time.
Isn't milligal like 10 to the minus 5 meters per second squared? But the point is that you're making, it's a very, very, very tiny amount that we're measuring the difference in gravity at different points. It's 0.00000, etc.
Exactly.
And maybe just so people know for technical details, this particular gravimeter, the older style ones would use a series of metal springs in a configuration that made the math work. We won't get into it. This one is a quartz spring. We're actually using the dielectric quartz. So how it changes due to force on the end of the spring and its dielectrical properties to be able to measure how much force is there and therefore gravity. They're interesting things, and we'll come back to them. I have more questions about them in a bit, but I just figured we were already there. We might as well do that.
Yeah.
Why not? Okay, but before we get into the science of the episode, I think it's important we talk about the sausage making of science. So the paper that I think you're about to submit, if you haven't already.
Hopefully in a few days.
In a few days. Is, well, by the time this airs, she will have submitted it, which is fantastic. It's currently titled Harnessing the Full Gravity Potential, Magmatic Loss and Recharge at Serra Negra Volcano, Characterized Through Joint Modeling of Gravity and Deformation Data. To publish a scientific paper, what are the general requirements before submitting it to a journal?
Let's start from the beginning, I think. So you have a problem, right? You have a scientific problem. For example, you have noticed that there are some changes in the gravity, let's say, before an eruption. So you pose a hypothesis and you say, okay, I think these gravity changes are related to something that is happening within the volcano before the eruptive activity. Of course, you're going to then go measure more or have your data that you have already collected. You're going to do some analysis. And then you're either going to prove or disprove your hypothesis, right? After you have...
How science works, everyone. That is
Exactly.
the description to a T.
When I said, let's go to begin, I said the beginning. So yeah, after you have already disproved or proved your hypothesis, you have written your paper. And it's usually, at least in the earth sciences, you're going to have several people working in the paper. Science, it's a very collaborative affair. So especially if you need to use expertise in different fields that no one can be expert on everything. So if you have other people working with you, those are going to be your co-authors, ideally, right?
Your co-authors have to agree or sign off on the paper to attach their name. You can't just write somebody's name down and submit a paper. They have to say they approve of what's in that.
Exactly. So you contact your co-authors. They have gone through your work, and usually that's going to take a couple of iterations, right? You're going to write a draft. It's going to go through your co-authors. It's going to come back with their comments, their suggestions, their corrections. Hopefully not, we don't agree, this is horrible. Hopefully it's going to be, oh yeah, this is great. I just think that you could add this and this and that. So after several iterations, everyone is going to be happy with the work, and then you are going to submit it to a journal. So you're going to submit it somewhere for it to be published and for it to be available to other scientists.
And then the journal takes that and assigns reviewers. So I guess it's the editor's job. And usually the editor is an expert in the field that you're submitting to. They may not know gravity, but they're going to be a geophysicist or someone who's worked on volcanoes using geophysics of some sort, right?
Yes, exactly. Or well, if you have chosen the journal correctly, that's going to be true. If you have chosen a journal, for example, in medicine, and you're trying to do work in earth sciences, you're just going to get what we call a desk reject.
Yeah, so the editor can make that first decision to reject or send on to the next stage of the process,
yes.
Which is the editors and the scary reviewer editor 3.
Yeah.
Okay, so let me sum this up. So first, come up with your hypothesis, you finish the data, the testing, you have something new or novel or something you can add to the scientific literature, then you write it up, you send it to your co-authors, and it's like an internal peer review, which can take months and months and months, never mind the collection of data, which could take years. How many years did this take?
So we have about 4 years of data just in this paper.
So the data took 4 years. The internal peer review amongst the co-authors can take anywhere from a month to a year, depending on who your co-authors are. And then you submit it to the journal, and then you get a editor, which takes a couple weeks to assign it to, assuming they don't kill it then, they assign it to editors. And then editors take several months to half a year. I know it shouldn't take half a year, but anyway, that's scientific publishing at its best. Before they give you an answer, sort of. So
yes,
what is the answer? The answer can be like kind of 3 different answers, right?
Yes, exactly. So the idea is that you get these editors, these scary reviewers that are going to go through the science, and ideally the main editor, the editor of the journal, the first one that receives the paper, is going to choose experts in the field that are going to go through the paper. They are completely objective, or at least as objective as possible.
Yeah,
yeah, exactly. And they are going to review that, of course, your methodology is right, that you have done everything as well as you could. Let's not say perfectly, but as well as you could. Your conclusions are sound, and well, that the science makes sense, basically. So it depends on what, after they read it, of what these reviewers thought about the paper. So either they can say, accept it as is. So they say, okay, we think that this is perfect. Just go ahead and publish it. We have absolutely no comments. I have not seen this magnificent
usually the closest we get is with minor revisions. That's the one I was looking for. That's exactly. Kind of like as perfect as it gets, and quite frankly almost never happens.
Yes, so you could get accepted with minor revisions, which is just okay. It's good. We just have these little comments. Everyone is going to have comments. It also means that they have gone through it with patience and with care to make it as, because this whole publishing process is so that the final work is at its best. It's presenting these new, everyone should benefit from it. The authors, the reviewers, and the final public, the person that is going to read this. You can also get accepted with major reviews, which is okay, we think that the general idea is okay. We think that the general science is fine, but we have concerns regarding the methodology, or we think you could do more to get this to the level of publishing in this journal. And then you have the very, very scary rejected, because they have serious concerns about the paper, and they don't think that with the work that you could do in the month or 2 months after you submitted, that you can fix them substantially for publication.
Yeah, it's always reviewer 3. The anonymous reviewer 3. So maybe now that I've said that, it's a joke, it's an inside joke. So you have the option as a reviewer to stay anonymous or put your name to it. Generally speaking, it is better to put your name to it. There are times where, due to conflicts of interest or other things, that you may not want to put your name to it, but it's always better if you're in sciences that if you're a reviewer, put your name to your review. That's just my personal opinion. Yeah, there's some nuance and caveats, but whatever. So that is how it goes. That's the publishing process. It is a long, drawn-out affair that, yeah, still some stuff gets through that never should, but it really does filter out the bad papers from the good papers most of the time. It's not a perfect system, but it mostly works. And because it is a system full of bureaucracy, we poke fun and jokes at it and complain about it. It's normal. So now we get to pivot to some of the technical stuff. Now that we did a little bit of the sausage making, Kilauea in Hawaii is a volcano most know about. It's on an island in the middle of the Pacific Ocean. It erupts runny, or if using the jargon of volcanology, low viscosity basalt. Check out episode 11 on Mauna Loa for more. And it also, Kilauea, erupts often. It's erupting right now. What about the subject of research here, Serra Negra volcano? How would you describe it?
It's pretty apt that you're mentioning Kilauea, because both Sierra Negra and the volcanoes of the Galapagos Islands, which Sierra Negra is part of, and the Hawaiian volcanoes are caused by the same geological process, which is a hotspot. Basically, you get a magma that is coming out in the middle of the plate, in contrast with what happens, for example, in the Cascades, where you have one plate coming into another, and then you have magma caused by that. In this case, you just have magma upwelling into the middle of plate and then coming into the surface. So Sierra Negra, it's a shield volcano, so it's similar to the Hawaiian volcanoes. It has gentle slopes, and it has a big caldera in the middle. It's very interesting because it has something called trapdoor faulting, which means that the center of the caldera can inflate. So it goes up with time in between eruptive activity.
Let me try to explain this, because I know I'm quite well aware of what trapdoor faulting is, but I don't think anybody else here is. So if you think of a trapdoor, you're standing over something and somebody hit a button and you fall through the floor. You have a hinge on one side, and then you have the flap on the other. So you're saying when you're having more magma, you're getting the flap moving up. So if you were on the trapdoor, you'd be rising to further higher.
Exactly. So one of the edges of the caldera acts as a hinge and allows the other to rise with magma. And then when there's eruptive activity, the trapdoor shuts down. So it goes all the way down, and then the process starts again. At Sierra Negra, there's about 10 years, 12 years in between eruptive activity, at least in these historic times that we are experiencing.
Cool. So is it due? I hate that phrase, by the way. I hate that phrase. But is the cycle getting to the point where we're expecting another one, or did it just happen? Or is that what your whole paper's about?
Well, it's kind of about that. The last eruption was in 2018. There are some very specific things that happen before eruptive activity that we can look out for, and that's why the Geophysical Institute of Ecuador is always monitoring the volcano. One of the characteristics of Sierra Negra, partially because of its trapdoor faulting, is that the caldera floor is always rising in between eruptive activity. So I don't know, maybe this is in the next, we're kind of jumping the gun a bit.
It's okay, we can do whatever.
Okay, so yeah, we are jumping the gun a bit, but in volcanoes, when the ground starts to deform, so it can, for example, move higher up, this is called inflation, it can go down, this is called deflation. These are usually signs that there's something happening within the volcano. This is one of the forecasting techniques for volcanoes, monitoring the deformation. So in the case of Sierra Negra, it's deforming basically all the time. The caldera floor, it's always rising. It rises at different speeds. So when it's closer to eruptive activity, it starts accelerating. So it starts rising faster. Because of the hinge of the trapdoor, Sometimes there's also sudden shifts in this deformation. So imagine that you have, I don't want to say linear because it's
So what you're
difficult to
saying is a
picture.
discontinuous, it tends to be constantly moving, but that rate of movement can be almost like the rate isn't continuous.
The rate is continuous, and then suddenly it's not.
Right, that's what I mean.
Yeah, exactly. I mean, the thing is, we know that something different is happening when that rate changes.
Right, and that's related. Okay, before we jump too far, because I think we're about to answer the next question that I really had on the list here, because it's important to always bring back research to its grand design, or what we're in the broad scheme of things and the trying to get to. And if we're going to take one particular aspect and look at a completely different problem and a completely different discipline as a way to get to from one small part to the greater whole, we could take cancer research where you're trying to maybe investigate ways of interacting with the immune system. Just understanding the immune system with the end goal of using that immune system and hijacking it to fight cancer. The goal is to cure cancer. That's not what we're obviously not trying to cure cancer here. Volcanoes can cause cancer due to the gases. But here, what is the larger goal here? We've been talking about deformation and it being discontinuous. We're talking about collecting data. So what, beyond this paper, what is the goal of collecting all of this data and trying to understand it?
So the idea is that the main objective of volcanology in general is to have a better forecasting of volcanic activity. You want to know if the volcano is going to erupt. Ideally, if you can even know how big is going to be the eruption, that would be best. And especially for the monitoring institutes, that's very important because they also want to, at the end, the important thing is that you want to save lives, reduce the risk of the people, communities living around the volcano. Now, this is not the job of just one technique. You use a lot of different things to do this, right? We already talked about monitoring the deformation of the volcano. With gravity, although it does detect, if you measure in time, gravity in the same spot in a volcano, it can detect changes in the mass. But most of all, with this paper, what we want to understand is how the volcano works as a whole in order to better understand the next period of monitoring changes, so that we can put it in context and then interpret better these changes and not just say, oh, something is changing, therefore something is about to happen.
Right.
Does that make sense?
Absolutely. I'm just going to put a little more context to it. So in the intro, I described a volcano's magma plumbing system. At play in your paper, we have deformation and gravity. Now, rephrasing what you said, in deformation, we get more magma to the system, provides pressure, and moves that trapdoor faulting, right?
Yes, exactly.
And so in that case, we're measuring the changing of where the surface of the Earth is, mostly within the caldera. I would imagine that gives us some idea of what's happening underneath, because that requires pressure, which requires magma or some other mechanism. In gravity's case, it's the same idea. More magma into the system represents an increase in mass, which changes the gravitational field at the surface, which you measure with your CG6 or CG5, sorry.
Yes, exactly. So the idea is that, yes, it's the same process, but they are different physical responses to the same process. So, for example, you get kind of like in a zit. I don't know if this is too gross, but if you get a zit, right, and it fills up with material, gross, but you get a bump, right? So then you know that there's more material, therefore is going to cause deformation in the case of the volcano. So you are measuring just how much the ground is being displaced, how much is moving. Then you go with the gravity meter and then you measure how much mass, ideally, how much material in terms of kilograms is getting into or getting out of the system. You also have measurements of gas, and therefore you try to understand, okay, what is the composition of what's changing beneath the ground based on the gases that are being expelled from the magma. in the surface. You also have monitoring of earthquakes, because if you have mass movement or movement of material beneath the ground, it's going to break rocks and is going to make earthquakes. And therefore, you can also locate where that is happening. You can try to pinpoint, for example, the depth. And depending on what types of earthquakes are being generated, you can try to know what is happening precisely beneath the volcano.
This is great. My normal set of questions are completely useless now. This is what happens when you interview a friend.
Sorry.
Hey, it's just as much my fault. Okay, well, we're going to do a little bit back and forth here because we've covered so much technical details already. But I do have one introductory question that I need to ask before we move on. How many magma chambers does Serra Negra have? Like, is there one and then there's something deep? Is there a whole bunch of small ones? Like, we know that there's something moving the trapdoor, but are we just really focused on one shallow one and that's what we can see? Or is there deeper ones? We know they exist, but we're not seeing them. We're not monitoring them in this particular study. Like, what's going on here?
Well, this is kind of going to tie up with my favorite scientific joke that I know it's coming. But yeah, I mean, it's we tend to simplify what's happening beneath a volcano into magmatic chambers, right? Into tubes, into little pockets of magma. It's not as simple, but it's completely necessary, at least for or limited data sets and or limited computer power in certain cases, right? At Sierra Negra, we know from the temporal changes in deformation and gravity that there is a shallow chamber. So about 1 kilometer below sea level, or about 2 kilometers beneath the surface of the volcano. So the higher part of the volcano is at about 1,000 meters above sea level. So about 2,000 meters below the surface of the volcano, there is what we model as a cavity with pressure, but it's actually pockets of magma at different stages of melt, so at different stages of it being able to be erupted. But this shallow chamber is the one that is storing all that nice material that every more or less 10 years at Sierra Negra that it's going to be erupting. But this is coming from somewhere. And from other studies that have done, they have tried to understand how the earthquakes travel throughout this volcano. And with that, they have mapped deeper into the volcano. They know there's a deeper magmatic chamber that goes from about 3 kilometers below sea level to 8 kilometers below sea level. And most possibly that is giving the material to the shallow chamber, which then eventually is going to be erupted.
So you just said that you're modeling and the shallow chamber, which is about 1 kilometer below sea level. Is there any other deeper chambers that are just not as affected by gravity and deformation?
Well, there is this deeper chamber that it goes from 3 kilometers to 8 kilometers. We just can't see from the gravitation with our methods or with gravity.
Right, because it's too deep and therefore the changes there are too small to measure at the Earth's surface with all the dynamic stuff going on due to the shallow one.
Exactly. At least that's my hypothesis, that we can, because there are changes that are so big because of this dynamic shallow system that they are hiding completely the smaller changes that are deeper below the ground.
And those changes might not be smaller. It's just the further you are, the smaller the signal. And so
exactly.
So on its own, time-lapse gravity, that's what we're calling it, or temporal gravity, that's where you took the meter and pressed a button on a spot and then came back a year, 6 months, 2 years later and to the same spot, set it up perfectly, everything is well calibrated, and you hit the button again and you got a change in gravity after making lots of corrections, right?
Yes, exactly.
Okay, so you have a difference in gravity. So let's pretend you're not on on Serra Negra. What other things can cause a difference in gravity in one spot over time?
You can have anything that is a change in mass or a changing the gravity field is going to affect the gravity meter, right? So before we think about anything happening beneath the ground, we have to think about all the other things that are causing the gravitational changes. For example, the influence of the sun and the moon on the earth. So that's why we have tides. We know that the tides are caused by the gravity of the moon, of the sun. The earth is orbiting the sun, the moon is going around the earth. So we have all of these gravity changes, all of these masses that are pulling at the sea, right? So all of this pulling to the sea is also happening to the gravity meter. And then there's also the mass of the sea that is moving closer and further away from your gravity meter or from wherever you are standing, right? And there is also a mass change. So it's an effect happening on your instrument. So you need to remove that. Anything that is environmental too, you need to remove. So for example, if you have changes in how much water is stored beneath the ground, just, the groundwater, just because you have precipitation, and some of that water is going to penetrate in the soil, and in a lot of places in the earth, there's a
Aquifer?
Yeah, an aquifer, I wanted to say a portion of the earth that is saturated, and yeah, that is called an aquifer. You have some water stored beneath the ground. And in a lot of places, that changes in time. It's not always going to be at the same level. Sometimes it's going to be lower. Sometimes it's going to be higher. And that is also mass change that is going to affect the gravity meter. Then anything that is man-made could affect the gravity meter. So for example, let's say that you are measuring near a quarry and you're blasting away rock and taking it away. Of course, that's a mass change, right? So it's also going to affect your measurement, even though it's not something super important for you as a volcanologist. You want to know mass change because of volcanoes, but now suddenly you have all of these environmental effects that you need to remove.
Yeah, I can imagine if the volcano collapsed somewhat nearby, you would have a bunch of material that has been moved downhill and changed its location, which would also change the mass that your gravimeter is measuring, right?
Exactly.
What about hydrothermal systems?
Exactly. So just as we were talking about groundwater, within volcanoes, there's a lot of fluids, just hot water that is stored within the volcano. And if the volcano has some changes in this hydrothermal system, for example, if it starts reducing because there's more heat that is evaporating it or causing it to leave the system, or it's causing a pressure change so that there's water leaving the system, then now you have less mass, and now you're going to measure some change related to that. But also, for example, at Sierra Negra, just because you have changes in the elevation of where you are measuring, because the ground is moving, so the ground is moving up, right? So you are getting farther away from the center of the earth. So it means that the gravity is decreasing just because there is some changes in where you are measuring, even though it's the same spot, but that same spot is not physically the same because of the activity of the volcano. But that is not necessarily related to the mass changes within the system. It's related to, yes, you are getting farther away from Earth, therefore gravity is going down.
Okay, so I think this is the last question on gravity specifically like this. How do you remove some of the environmental effects like water levels? So the water, you had a big heavy rain this year, so your water level's higher. How do you remove that or reduce the effect on your data set? Because you're trying to measure mass changes of only the volcano.
That's where we start getting in trouble.
Well, for sure, but there must be what assumption can you make? And assumptions always have to be listed. They're made all the time in physics and geophysics and volcanology, because you have to assume things to make things simpler, whether that's geometry, like it's a sphere, or weightless, massless cow, or as I understand it, that you've told me the joke in Espanol is a weightless, frictionless chicken.
Yes.
But in a gravity survey, one of the ways, as I understand it, we can try to remove some of this is by having a base station that is outside of the dynamic area, so that we make an assumption that all the water is the same everywhere, right?
Yes, exactly. So well, you can do it in several ways. The best way would be to actually be measuring stuff. So you would have some wells, and then you would be like, oh, the level changed this much. Therefore, I can calculate how much that mass change is in its gravity change in my stations.
Porosity percentage, et cetera, yeah. We never have that, though.
We never have that. The other thing that you can do is, if there are some data from the meteorological institutes of the area, you can try to say, okay, there was this much precipitation. Let's assume that the whole precipitation is going into the aquifer. Let's get more or less the porosity of the area, and let's measure what is the upper range of how much gravity is going to change because of this precipitation. This is assuming that a lot of assumptions. First of all,
what you're saying is you need a hydrologist to come on board to start helping.
Yes, exactly. Or you can get a couple of stations farther away from your area of interest. And as you measure the gravity in the stations of interest, you also measure the gravity of these stations in comparison to stations that are farther away. And then you can say, okay, these stations farther away have changed this much. And this is probably just because there's been some changes in precipitation or things like that. And then you can assume that that change is not related to the volcano and just take it out. But you have to be very careful about that too.
Yeah. In other words, there's a lot of unknowns, and that's the nature of geophysics. There's always unknowns, whether you're doing inversions, which is an ill-posed problem, meaning there's an infinite number of solutions that can actually give you what you saw in your data. But there's only so many that are reasonable and geologically understandable. They're not, and that's just the nature of it, I guess.
Yes, exactly. So the thing is, I like the idea of doing more of these things. So don't do just one thing, do several. That way you have redundancy, right? So if you can do, okay, let's just do some quick calculations about using just the precipitation to see, okay, what would be my biggest change caused by changes just in the groundwater from precipitation. And then if you see that it's very little, then you can just forget the whole thing. But you always want to check your gravity with other farther away stations, even if you are not thinking only of groundwater, because the instruments can fail. The instruments can have what we call systematic errors, which has happened to me in the past. So one day the CG5 just decided to be temperamental and did not measure what it was supposed to measure. It just measured something completely different. But we realized that it was not measuring something that was true, that was not the actual measurement, but it was something related to the instrument, because we had done check with other stations that were supposed to be stable. And at that point, if those stations are not stable, they are very close together, therefore, if there's changes between those stations, there's some sort of instrumental problem, and we have to go back to square one.
Yeah, the instrument can apparently screw up on you for a number of different reasons, and one of the ones that I find most interesting that you never see coming is a teleseism. So for those, yeah, see, she laughs instantaneously, because we all know when this comes through and you're just like, what is going on? What broke my meter? And then you go, oh. So a teleseism is a large earthquake that happens somewhere else outside of your area of interest. You have no idea it's going on, probably because you're in the middle of nowhere without internet, so you have no idea. But the ground is still moving, and it's moving enough that it is completely swamping your signal. You can just see the numbers on the gravimeter kind of go up and down and up and down. And the only way you can notice it's a teleseism, in the cases of this particular meter, it has a graphical display, so you can see the gravity in real time, and it will show up to the sinusoidal wave, a whimsical wavelength, if you will. For other meters, which do not have this graphical display, you have to like watch the numbers go up and down until you can like piece together the sinusoid in your mind. Or if you have internet on your phone and you happen to be close to a cell tower, you can just go to the USGS website and look for big giant teleseisms, and it can take hours for these things to disappear. But it just goes to show that these things are temperamental, and basically every crew that I've ever been on, we have a nickname for the gravimeter, because we don't call it the gravimeter, we call it the
baby.
Yes, because it's always throwing tantrums.
You also want to take care of it as a baby, because the instrument itself, it's very, very prone to screwing up if you shake it. So don't shake your baby, any baby. Don't shake babies, please.
Because it's got a spring in this particular case, right? Like if you shake the spring, you can change the size of the spring and create data problems for yourself, because you're no longer measuring the spring properties change essentially.
Exactly. And the spring needs some time after this to go back to normal, basically. This is difficult if you are walking on top of a fresh lava flow that it's basically bunch of broken glass that goes down. Basically, you step on something and then you are stumbling 2 out of 3 steps. So falling down, it's a possibility. You're carrying the gravity meter, suddenly you have, through no fault of your own, shaken it, or it has basically changed position in an abrupt manner, let's say.
Yeah, and that used to be a much more of a bigger problem back in the day, using the old spring gravimeters, because they would get shaken a lot easier and have issues with the data. Gravity, mass, after you control for things like the change in the height of the location, you took the gravimeter multiple times, the tides, earth tides, as well as what we call ocean loading. That's the idea that the ocean mass being affected by the earth tides is a mass that's closer and farther away from you. You correct all of this and you get a mass change. On the other half of your paper, you're using deformation, and that's the trapdoor felting. So that data set, were you using only GPS or were you using INSAR? And if you were using INSAR, spell out the acronym for me.
Okay, so we were using GPS, just GPS in this paper, but this paper has gone through many iterations, as we mentioned before. That's just the nature of the beast. So during my PhD, I was using also the INSAR signal, which is interferometric satellite aperture radar, which basically you measure how you send from a satellite a radar signal to the Earth. It comes back to the satellite, and then in a subsequent round, the satellite goes over the same spot again, sends the radar signal again to the same spot, or in this case, you basically get pixels, as in a picture, and you compare that radar signal, and that is going to give you the distance that signal travels from the Earth back to the satellite. If there has been some deformation, that distance is now different, which means that you can measure through that difference how much the Earth has moved.
Essentially, you're taking the waves of the satellite in one position, then you repeat the same measurement at the same position at a later time, and then the phase difference between the waves is what you use to measure the amount the Earth had moved. It all comes down to wavelengths.
It all comes down to wavelengths. Everything is a wave.
In this particular instance, though, you just used the GPS data. And I guess is that like you use the gravimeter and you're taking points, or is this continuous GPS? You have something somewhere and you're just always taking readings?
Yes, so there is a continuous GPS network installed at Sierra Negra, which means that there's a lot of GPS sites that are all the time just collecting the position of that point, and looking at how, in the case of Sierra Negra, how that is going up and up and up. The reason why we decided not to use at the end INSAR, although it's very, very useful, because you don't need a ground network, you need the satellite measurements that are worldwide available for a lot of the places in the Earth, is that at some point, during Sierra Negra's eruption, there was so much ground movement because of the eruption that it rendered these measurements useless. So although INSAR is very, very powerful, it also means that, well, I don't want to get too technical with it, but this difference between the radar signals, if it's too different, then you cannot decode it anymore.
Yeah,
So
we call that incoherence in the image, because it actually provides an image based on the phase. So if the phase is too different, you get incoherence. Or if you get something that reflects phase or reflects light in different directions instead of just a shift, it also becomes incoherent. So hot lava flows cool and change shape so much that they show up as incoherent on INSAR images. But I didn't realize that there was so much deformation over this short period of time, because they come by every week, every couple of days. I'm not sure how often you're able to get INSAR in this place of the Earth, but whatever that repeat time is, the deformation was so big that it created an incoherent image, too much phase change, and then you couldn't use it. That's wild.
Yeah.
How much are we talking about? We're talking like meters, tens of meters. How much we talk about?
Yes. So during eruptive activity at Sierra Negra, the ground in a few hours to maximum days, but most of the movement happened during the first hours of the eruption. The ground sank about 8 meters in the center of the caldera.
That'd be enough to feel. Like you would actually notice you're going down.
Yes.
If you were standing there, you'd be like, "Oh my gosh, what's happening here?"
No one was standing in there.
No, nobody should be, because you might die and get run over by a lava flow or asphyxiate to the volcanic gases. I'm not suggesting someone stand there. But that's a rate that standing there you would feel, and that's pretty wild.
And actually, you can see new cracks in the earth. So basically, almost like little faults because of these subsidence that happened so fast that it cracked the earth, and it caused some cracks all around the edge of the volcano, of the caldera.
Crazy. It's 8 meters. Damn.
It's a lot.
It's a lot. It's a pretty big area. It's not like 8 meters on like one spot as you cave into a little hole. This is like a whole trap door. Like it's
about 10 kilometers across. So you have all these circular with a diameter of 10 kilometers, more or less. 10 or 20? Let me check. We can go back to that specific, but it's a big area that it's going down.
It's a big area, and I got you off guard. This wasn't as you didn't know I was going to ask that question. I didn't know that it was 8 meters, although maybe it was in the paper and I missed it. That's my fault. So you've got the two different data sets, and of course, in my day job as a geophysicist, I want to take many data sets and invert them together. I want to use multiple data sets to constrain one another, and I'm assuming that's what you're doing here, because as computers get more powerful, we're able to do more complex modeling, and volcanology is no different. However, there's a lot less money in volcanology than there is in industry. So solving the physics of two data sets simultaneously is, in my understanding, of why you've got the deformation and the gravity at the same time, and is all part of that paper. How hard is it? And why did you really need to solve both of them together?
So here we need to go back to what we were talking about with the deformation and gravity, right? So for deformation, we are assuming that you have a volume change and a pressure change within a cavity. So you have to think about a balloon, right, that it's inflating. It's not only inflating because it's getting air inside, it's also inflating. For example, let's say that you have a closed balloon, and then that balloon, you get it into a different temperature. The pressure inside the balloon is going to change because of the ideal gas law. So the size of the balloon is going to change too. It's kind of same-ish in the case of a volcano. You can have volume inside that is causing the deformation, but that volume has also pressure. Is pressing into the chamber and is causing deformation. So just with deformation, you cannot know how much is inside because you now have two different causes of deformation at the surface. You don't know exactly how much mass is responsible for that just from how much deformation is at the surface, because it can all be because of volume change, it can all be because of pressure change. This is not in the sense that in reality, there's always going to be a combination of both. Only pressure change, only volume change, it's not realistic. But that means that you cannot just say, okay, this is the amount of volume. I assume that this is magma, therefore it has more or less this density, and voila, we have mass. That is a flawed argument. You can do it if you don't have the measurements, but you have this assumption behind it. That
Yeah,
you
you're
know
putting
that
the two end members and saying, well, it has to be between here, right? That's what you're suggesting. But because you have both, you don't have to do that.
Exactly. And with gravity, at the same time, as we mentioned, just because there is deformation, there's going to be gravity change. So if you don't monitor the deformation and you just measure the gravity and you say, oh, all this gravity change is due to mass change beneath the surface, so there's more material or less material, you are completely missing the effect from just the floor going up and down and changing your gravity because of that. But there's not only that. Because the ground is deforming, there's a lot of wacky things happening with the rocks that surround this chamber. So you don't only have that your gravity meter is moving up and down by itself. You have all of these rocks that are moving with it. And that is already causing also a gravity change. Then around the chamber, because rocks are getting at the end kind of pushed and moved, sometimes it can also mean that the density of the surrounding rocks is changing because now you are compressing them, right? You're making them more dense. And in some places, they are getting less dense because there's some interesting things happening around that. And in the past, we had trouble measuring all of these effects. We knew that more or less, just because the gravity meter was moving, the Earth is moving up and down, there's going to be a gravity change approximately to a number, a constant times the amount of elevation change, of vertical deformation. But all of these other effects that I'm mentioning, usually we either resorted to very, very basic simplifications, or we just assumed that they were too little to be seen. But that's not the case at Sierra Negra, where we have meters of ground deformation. Even the little changes in density around the chamber, or the mass moved and replaced by the contents of the chamber, all of these things are going to contribute to the gravity change at the surface, where in other volcanoes it might not be as evident. However, we can use both deformation and gravity at the same time to constrain these effects.
Okay, so now for the mass and volume, what was the outcome of this study? I mean, how much mass or loss or gain in reference to what was actually going on activity-wise? Is there a way to say something that's even more mind-blowing than 8 meters of deformation?
Well, I don't know if, because sometimes it's difficult to understand large numbers, right? But what we can say, for example, we saw that when we compared the gravity measured in the center of the caldera after the eruption and just before the eruption, we saw that the mass that was lost from the system was equivalent to what we saw in the lava flows during eruptive activity. Now, this might be like, oh yeah, of course, you have an eruption and now you have things that have gone out and now you have the same amount that has gone out in outside. Woohoo, it's not that impressive. But it is impressive, first of all, because we are checking that what we're measuring is right. It makes sense. That's always a win. It's not always the case sometimes because of the multiple complications that we have already talked about. But also we are seeing that a lot of this mass is not being replaced immediately in the system. So we can start looking at where this mass is also coming from. So most of the mass that was erupted came from this shallow chamber. So it's not coming from another chamber that we don't know about. It's not coming from something deeper. It came from this shallow chamber where we measure the change, the gravity change. In terms of the amount of mass that has gotten into the system, we also realized that, first of all, immediately after eruptive activity, so after the eruption ended, the mass within the shallow chamber started to increase again. So the gravity started to increase again, and this is not only because of the deformation, but yes, there is mass coming into the system after the eruption. We also saw that the rate of change is less as time goes on. So immediately after eruptive activity, there was more mass coming into the system per year than in the next 3 years after the eruption. And what we also know is that if the last rate of mass increase that we measure is maintained, then in about 10 years after the eruption, so from 2028 onwards, the mass that was lost during the eruption will be recovered in the system. So potentially, I'm not saying this is the case because we need more evidence, but potentially we now have some idea of when to start looking for dramatic changes in the system that might be caused by the magmatic chamber, going back to how it was just before the eruption in 2018.
Yeah, I guess because I'm just going to go off on another tangent, even though we're going probably way too long. And no, I will not make this a two-parter. But so in Hawaii, for instance, Kilauea, since it was such an apt comparison earlier on, it doesn't erupt the same amount of material that comes into its central magma system. In fact, some studies have put it up towards of 70% of all the magma coming in gets like put in as like intrusive bodies, which means just an area underneath the ground that magma gets stored and cooled instead of being erupted. So this is actually pretty crazy to me to say that the flux coming into that volcano, almost all of it is actually being erupted during these eruptions.
No, I don't think we're saying that. What we're just saying is that the amount of magma that was erupted in 2018, that is going to be recovered in about 10 years. I don't know if we can say that because we don't know how much magma, because we don't have measurements before that, before the eruption in 2018. So we don't know if there was more into the system before it erupted. So we don't know if the amount of magma that it erupted is 100% what was recovered before. We know how much time is going to, we can assume how much time is going to need to revert, to go back to the mass that was lost during the eruption, but we don't know if that is exactly the mass that is the whole thing is being erupted then. Does that make sense?
Yeah, that's fair, but even still, you're suggesting that you're within error bars of what you first measured got erupted.
Yes.
Which is still impressive to me, coming from other volcanic systems where it's usually clear that you're erupting way less than what's coming in. We can look at Masaya volcano in Nicaragua, for instance. We know that there's lots of material coming in because it degasses all the time, up to 10 cubic kilometers of material of degassed and not erupted. So it's almost the norm in these really active volcanoes that they erupt less than what comes into the system. It seems like Serra Negra might be odd in that regard, that it at least is close. Or are we just looking at too short of a window instead of looking at the full time of geologic time?
I think we are looking into a short window. I think if we manage to get more data sets until the next eruption, if there then is a next eruption, because that is not even certain, right? But if we get some more gravity measurements, and now we do have this whole change in time, then we can start saying more things in that regard for sure. Sadly, there were some measurements, gravity measurements before 2018, but they were done with a different instrument, and we have no way to link these two surveys together. We tried, but we realized that we weren't getting anywhere, to be honest. And that's part of why this paper has gone through so many iterations.
Ah, history, standing on the shoulders of giants.
Exactly.
Okay, so that does lead into exactly the next question before we really wrap up, is how does this help with the larger goal of eruption forecasting? I mean, you and I were just kind of spitballing about it right there, but how do you see this as a plank, a screw, a sliver, whatever you want to call it, towards that lofty goal?
So specifically at Sierra Negra, now you can start looking into the amount of recharge into the system in terms of mass. You can know, okay, in 10 years, more or less, or if we measure gravity and the rate changes, but we can know how much mass is getting into a system, we can estimate, okay, now we have recovered all the mass that was erupted. And are we now getting into closer to eruptive activity or no? Do we need to look closer into some signals or no? Now we have a way to also pull this data, and this is why science is such a big collaborative effort, that we can put this data into models of stress in the system. And that's something very cool that other scientists are doing, that you get data coming in real time. You look into how much stress the rocks, the system is in, and you see how close it is to failing. And you can start trying to do a dynamic forecasting using data real time to get into how close the volcano is to failure. Of course, this forecasting is always has some, you need to take into account all the errors of the different data sets, the errors of the modeling. There's big caveats, and you're never going to be able to say, okay, it's in 2 days at 10 a.m. In a sunny day. No, that's not going to happen. But you can at least say, okay, in a short-term scenario, we expect that the system is close to failure, or in a medium term, or try to estimate how much more it would need to get it to failure. That's for Sierra Negra. In terms of the bigger picture, what we have done with this paper is to, instead of doing first the deformation, calculate how much that affects the gravity, and then use that gravity to estimate how much mass. We have used the two data sets at the same time, and without introducing more error by doing this sequentially, but doing it at the same time, we have managed to estimate both the volume change and the mass change within the system. So how much material went in, it's estimating in the density of the material, and how much there was of space change within this magmatic chamber. So this is something that now can be used in other volcanoes, in which maybe it's too difficult to have a continuous GPS system running all the time, especially with the gravity stations, but maybe you can have measurements in other places. In the past, because you needed to do this calculation before doing the gravity, we used to do that. It meant that you needed the exact same spot, you needed to measure the deformation, and you needed to measure the gravity. Now you don't need to do that. You can have two different data sets in different positions in the volcano, and then combine them during the modeling. And it's still, because you're assuming, here comes the big assumption, you're assuming that the effect is caused by the same thing, then you can use these two elements to go to the same answer, and it should be correct. You should be calculating also this volume change deformation effect on your gravity datasets. So this has implications for other volcanic systems. So maybe it will make it easier for other observatories where there may be some constraints on how and when you can do the measurements, to do gravity and to estimate mass change within the ground.
Yay. No, I'm serious. That was cool. That was cool. just geeking out over here. I mean, it's in my wheelhouse too. I'm so glad to see it move forward.
Yay. Mhm.
Is there anything else that I have forgotten to ask or you wanted to add about your work, or perhaps a plug for future work or anything else you're working on?
Just a caveat that this jointly modeling of the formation and the full gravity signal without this correction, it's only possible if you have changes of both deformation and gravity because of the same thing. Right now, we're working in some different volcanoes in Ecuador, specifically at Cotopaxi volcano, which I already did my master's on. And we saw that the deformation was showing effects from one thing, and the gravity actually measured changes in the hydrothermal system of Cotopaxi, which is very developed. It's a glacier-clad stratovolcano. So there's a lot of water beneath the ground. There's a lot of hot fluids that were moving, and they are closer to our gravity sites. And therefore, we did not see anything related to the magmatic system, but we did see changes in the hydrothermal system. So of course, with science, this is always the case. There's no one solution for things. You need to go and try. As we mentioned before, hypothesis, you prove it, you disprove it. In the case of Cotopaxi, we saw that whatever the deformation was measuring had almost no gravity signal at the surface, but we did have gravity signal at the surface. Therefore, what is happening? At Sierra Negra, we saw that there was up deformation and up gravity or down gravity, and then the opposite. So it was definitely, we hypothesized, yes, this is related. This is mass change within the shallow chamber. And then with the modeling, with the joint modeling, we found a solution that we pose. It's giving a reasonable explanation for what's happening in the system. A geologically sound explanation. So always, there's no one size fits it all, and science, it's always evolving in that sense.
Okay, first, before I ask the final question, thank you so much for coming on. I didn't have to twist your rubber arm at all. All I had to do was ask, and you jumped on it. You have to send me updates about when this paper finally gets accepted, so that way I can also plug it here as like something that happens on the show. So, you ready for the last question?
Yes.
Okay, and as everyone should know, because I've mentioned it before, I warn every guest that this is the quintessential last question, and if they listen to the show, they would have also noticed that I say this every single time. So what is your favorite science joke?
I think you may have already had it on, but I'm going to say it anyway. So, and this is tying everything together because we always make assumptions in science, right? There's a farmer, and his cows are not happy. They are not giving enough milk. He changes his amount of food. He changes the conditions of the barn. He changes as much as he can think of, and still the amount of milk that the cows are giving is going down and down and down. Therefore, he contacts a nearby university. And he says, well, I have a problem. I have no idea what is happening. My cows are not giving as much milk as they should. So the university sends a team of scientists, and within this team, there was a physicist, there was an engineer, and there was a sociologist, I believe. So after getting a lot of data, the scientists go around, take samples, and then go back to the university. After a month or so, they come back to the farmer. So the sociologist has a couple of explanations related to the amount of entertainment that the cows are getting. So the farmer takes that into account, moves on. The engineer brings up a beautiful model of how the cows move, how the cows eat. It has a lot of nice visuals, but at the end, it doesn't give any information about why the milk is decreasing. And finally, we get to the physicist, and the farmer says, okay, so do you have a solution? And the physicist says, I do have a solution, but it only works if your cows are in a vacuum and are perfectly spherical. So that's I don't know how
Oh
to
my
tell
goodness.
jokes. I am sorry.
That's half the fun of it. That's why I do it. I mean, it takes people off of their super serious, stuck in the science ways, and it breaks up a conversation about volcanoes, death, destruction, looking forward to the future and forecasting eruptions. It's a beautiful way to break everything up and make it very, very silly. You can tell I love Monty Python. Okay, thanks again for coming on, and
Thank you so much, Jeff. This has been so much fun. I always like to prattle about volcanoes and gravity, especially gravity.
okay, that's a wrap. I'm going to cut this really short as I can because this was an extra long one and I just didn't want to cut it into two and make it shorter than it needed to be. But thank you so much for getting all the way through it. If you like the show, if you haven't already, please subscribe. I mean, come on. And tell a friend. Support the show. More than anything else, give me some feedback on social media. Give me a poke. Tell me a joke. Yes, tell me a joke. Okay, I'll see you guys in 2 weeks.
Lost in the fog of the cosmic storm, floating on whimsical wavelengths is the norm. Dancing through the stars, chasing spectrums of light, riding the waves that are just out of sight. In a world so chaotic that misbehaves, melodies that echo show us sex always. Colors intertwine, painting the sky. We're lost in the rhythm as the universe flies by. Oh, we're tuned in, feeling the beat of the unknown. Can you hear it? It's echoing through your bones. In this melodic maze, we let